Welcome back to Dreams of Earth, where we explore the universe one gentle contemplation at a time. Tonight, we embark on a tranquil exploration into a fundamental cosmic inquiry. Where does space conclude? This question, initially appearing straightforward or even amusing, reveals itself to be profoundly thought-provoking, expanding the mind much like the cosmos itself. My hope, as always, is that this presentation aids you in finding gentle repose, or at minimum, offers a cosmic perspective on your concerns by journeying back several billion light years. Naturally, there's a slight possibility it proves too captivating, preventing slumber. Should that occur, consider it a bonus of acquiring fascinating knowledge. Before we journey among the stars, please consider liking this video and subscribing if you haven't yet. Your support genuinely helps this tranquil channel expand. I'm also curious to know your current location and time. Perhaps you're viewing from a comfortable bed in Stockholm at 11:30 p.m. or perhaps from a Melbourne couch at 3 p.m., feigning productivity. Share in the comments below. It's truly delightful to connect with our contemplative community spread across the world. Now, unwind. Make yourself comfortable. There's no need to retain specifics, jot down notes, or remain acutely attentive. Simply allow the narrative to envelop you, much like the gentle cosmic background radiation. As we commence this serene exploration into the boundless unknown, please note this video is exclusively for educational and relaxation purposes, not medical advice or a replacement for professional care. Prepared? Let us start. What precisely defines space? That silent, dark expanse visible when we gaze at the stars. What is its true nature? Many perceive space merely as an absence, a void, a vast emptiness where celestial bodies drift, planets revolve, and socks inexplicably disappear. Yet, space, contrary to common belief, is far from empty. Indeed, it stands as one of the universe's most dynamic, enigmatic, and frequently misconstrued elements. Let's first revisit fundamental concepts. For centuries, space was envisioned as a mere backdrop. Picture a theatrical stage. Space constituted the flat wooden floor, with planets and stars acting as the performers moving upon it. This perspective largely stemmed from Sir Isaac Newton, who posited space as absolute, an unyielding, static arena for all occurrences. Time progressed uniformly for all, and space served simply as the three-dimensional framework containing everything. Then appeared a man of disheveled hair, known for his blackboard scribbles, Albert Einstein. He dismantled that neat conception, substituting it with a notion considerably more peculiar and refined. As Einstein proposed, space is anything but a passive setting. Instead, it's a vibrant, pliable fabric that flexes, contorts, and distorts in response to mass and energy. This spatial dimension, intertwined with time, constitutes a four-dimensional entity known as space-time. Crucially, this dynamic stage actively reacts to the events unfolding within it. To illustrate, imagine a trampoline. Position a bowling ball at its center, and the fabric sags. Now, propel a marble across the surface. Rather than traveling linearly, it follows the curve of the depression. This somewhat mirrors gravity's function in Einstein's cosmos. Enormous bodies, such as stars and planets, curve the surrounding space-time. This very curvature is what we interpret as gravity. Our descent toward Earth isn't due to a magnetic attraction, but rather because Earth has distorted space-time, and we are effectively rolling into that depression. One might now ponder, very well, space distorts, but in its apparent emptiness between stars, isn't it simply nothingness? entirely. Even within the most desolate, isolated reaches of the cosmos, space remains vibrant. Due to quantum mechanics, we now grasp that empty space is fundamentally not empty. At the most minuscule conceivable scales, considerably smaller than atoms, space teems with what physicists term quantum fields. These fields are not objects residing within space. They are space. Each particle in the cosmos originates from its associated field, an electron from the electron field, a photon from the electromagnetic field. Even in the absence of particles, these fields are never entirely quiescent. They incessantly fluctuate, generating minute, transient particles that materialize and disappear akin to cosmic fireflies. This inherent, restless energy in empty space is termed vacuum energy. It resembles the surface of a pond. From afar, it appears serene, but closer inspection reveals subtle ripples, perturbations, and sporadic jumping fish. What appears seamless and devoid of features from a distance is in reality replete with concealed activity. Hence, physicists assert that the vacuum is not void. It pulsates with potential. Particles spontaneously emerge and recede in ephemeral pairs, termed virtual particles. Though unobservable directly, their influences are measurable. For instance, they affect electron behavior near atomic nuclei and even contribute to the enigmatic phenomenon of dark energy, thought to be accelerating the universe's expansion. Therefore, space is not merely a receptacle for misplaced keys or stray thoughts during uncomfortable silences. It is a vibrant entity, teeming with structure and motion, even when visually devoid. Furthermore, it becomes yet more peculiar upon realizing that space itself is capable of expansion, not objects within it moving apart, but the very fabric of space stretching between them. This concept, also derived from Einstein's theories, forms the bedrock of our contemporary cosmological understanding. But let's take a brief respite. It's understandable to feel daunted by the notion that existence's most ostensibly empty component actually vibrates with unseen energy, geometry, and fields. Yet, paradoxically, this can be profoundly reassuring. It implies the universe is not solely a frigid void. Even in its most serene, darkest instances, activity persists. A gentle background hum, akin to a soft fireplace crackle or the rustle of leaves on a calm evening. This hum, these fluctuations, this ceaseless vacuum, serves as a testament that space is more than merely the absence of matter. It is a tangible entity possessing inherent characteristics. It can curve and extend, expand and ripple. It holds energy. It possesses temperature. Indeed, even the immense emptiness separating galaxies is believed to maintain a temperature just a few degrees above absolute zero, subtly warmed by the residual luminescence of the Big Bang. Thus, when we pose the question, what is space? We're not referring to a blank void. We're discussing an intricate, structured medium that interlinks every atom, every galaxy, every living entity. Space isn't merely the setting for events. It is an event itself. It's integral to the narrative, not just the backdrop. And perhaps that is the most astonishing revelation. The deeper our examination of space, the more it defies emptiness. It contorts, it resonates, it wavers, it expands. Even in its apparent inactivity, it is never truly dormant. And regarding those elusive socks, space may not be the culprit. However, if they did indeed tumble into a region of distorted space-time, they would at least join a rather exclusive scientific enigma. Envision yourself atop a serene hill beneath a clear night sky, contemplating a universe extending infinitely in all directions. It appears boundless, immeasurable, everlasting. Yet, what if I revealed a cosmic boundary to our perception, a kind of cosmic enclosure encircling us? This isn't due to the universe concluding there, but simply because light from beyond hasn't had sufficient time to reach us. This is not speculative fiction. This is the observable universe, the segment of the cosmos we are capable of detecting. This includes light, radiation, gravitational waves, essentially anything that has journeyed to us since cosmic inception. The term observable is crucial. It does not imply the non-existence of everything beyond it. Rather, it signifies we haven't yet been fortunate enough to witness it. Herein lies a fascinating complexity. One might logically assume our maximum viewing distance would approximate 13.8 billion light-years, given that is the universe's approximate age. And if light travels at its defined speed, wouldn't that mark the limit of our sight? Alas, the universe is not so simple. Due to the expansion of space itself, that boundary extends considerably further. Our observable universe presently has a radius of approximately 46.5 billion light-years in every direction, resulting in a span of roughly 93 billion light-years. Indeed, you heard correctly. Despite the universe's age of only 13.8 billion years, the distance to the most distant galaxies we can perceive exceeds 3 times that, because space has been continually expanding. Consider this analogy. Envision raisins placed upon a loaf of bread, then baked. As the bread expands, the raisins drift further apart. Now, picture a photon of light emitted from one raisin towards another, just as baking commences. By the time the light reaches its destination, the bread will have expanded significantly. The photon's path was not over a fixed distance, but across an ever-increasing one, with its target receding throughout the journey. This broadly illustrates what occurs on a cosmological scale. This leads us to the cosmic horizon concept. It's not a physical barrier. You won't pilot a spacecraft and unexpectedly collide with the universe's edge, as in a cosmic animation. Rather, it resembles a gradual diminution of information. Past this horizon, light from remote areas simply hasn't had sufficient time to traverse the distance to us since the Big Bang. We are, in essence, within an immense fog, discerning only the immediate luminescence. The remainder remains obscured, not by absence, but because the universe has yet to transmit its signals. This horizon delineates the perimeter of our observable universe, a boundary perpetually in flux. With the passage of time, light from increasingly distant regions will arrive, causing this observational bubble to grow. Simultaneously, due to the accelerating expansion of space, certain galaxies are receding from us at such velocities that light emitted by them now will never reach us, not even over trillions of years. Their recession speed surpasses that of light itself, not through violating any cosmic velocity limit, but because the intervening space is stretching too rapidly. The universe is, in a profound sense, gradually receding beyond our reach. Let us now pause for a moment to contemplate something remarkable. Each individual star, every galaxy, every faint luminescence visible in the night sky, lies within our observable universe. This is the encouraging aspect. The less sanguine truth is that an immensely greater, perhaps infinitely larger expanse almost certainly lies beyond it, forever unseen, untouched, and unstudied by us. We are enveloped by a magnitude that renders our instruments humble. Nevertheless, we can only peer through this small perceptual bubble. Even more humbling is the realization that every observer, irrespective of location, possesses their unique observable universe. Were you situated on a galaxy 10 billion light-years distant, Your cosmic perceptual sphere would partially intersect with ours, but also encompass territories entirely unknown to us. Fundamentally, the observable universe is not the universe. It is merely our perspective of it. And what an incredible perspective it is. Approximately 2 trillion galaxies, each harboring millions to trillions of stars. Such an immense quantity of starlight is contained within our modest observational sphere. Photons from some of these galaxies have traversed billions of years, only to ultimately be absorbed by your retina or a telescope sensor. This very night, some of that light commenced its voyage before Earth's genesis. That primeval luminescence functions as a form of time machine, a sealed message from a bygone era. Yet, despite the richness of this observable universe, it likely constitutes only a minuscule portion of the total cosmos. Past the cosmic horizon, space could conceivably extend infinitely. It might be curved, flat, or even fold back upon itself in an exotic, multi-dimensional configuration. However, we shall never ascertain this, neither through light nor any signal constrained by time and the limits of causality. There is a certain tranquility in this limitation. The awareness that we cannot perceive everything underscores our fundamentally local position within the cosmos. We need not comprehend or command the entire universe to derive meaning from it. At times, it suffices simply to sit beneath the stars, cognizant of being part of something immeasurably grander than ourselves. And while 93 billion light-years sounds immense, which it is, it represents merely the perceptible veneer on an incomprehensibly vast cosmic cake. What lies beyond? We can only speculate. Perhaps more galaxies, more intricate structures, more dark matter and dark energy, or perhaps something even more extraordinary. For now, however, we reside here, gently carried within a luminous sphere of light, data, and time. A sphere defined not by boundaries, but by the patient traversal of photons and the constraints of cosmic chronology. It is not a confinement. It is a blessing. A slowly enlarging blessing that permits us to delve further into the universe's ongoing narrative with each passing day. When observing the nocturnal firmament, we frequently assume we are witnessing the universe in its present state. This, however, is not entirely accurate. What we genuinely perceive is the universe as it existed in the past. Each star, every galaxy, every luminous point in the sky, functions as a temporal capsule. The greater its distance, the more ancient the light we are receiving. Indeed, surveying the universe is akin to sifting through a cosmic attic, with each successive layer of light guiding us further into antiquity. Let's begin with the fundamental unit, the light year. The distance light traverses in a single year, roughly 6 trillion miles, or almost 10 trillion kilometers. When you gaze upon a star located 100 light-years away, the photons reaching your vision departed that star a century prior. You are observing it not in its current condition, but as it appeared during the youth of your great-grandparents. Extend this concept across the immense breadth of space. Certain galaxies we perceive are situated billions of light-years away, implying that the light we detect from them commenced its journey prior to the very existence of our solar system. Long before Earth formed its oceans or cultivated its initial microbial life, that light was already speeding towards a future beholder, towards you. This introduces what astronomers term look-back time, a metric quantifying how far into the past we are observing when we view remote celestial bodies. For a galaxy 8 billion light-years distant, its look-back time is 8 billion years. That light has traversed space for over half the universe's age. reaching us precisely to illuminate your nighttime observations or impinge upon the mirrors of an Earth-orbiting telescope. Peculiarly, space is replete with spectral vestiges, echoes of past states. We are not witnessing galaxies as they appear today, but rather as they were, preserved within earlier phases of their being. Some might even have ceased to exist, perhaps merging with other galaxies, altering their form, depleting star-forming gas, or simply drifting beyond light's reach due to cosmic expansion. Our perception is of a kind of cosmic fossil record, inscribed in photons. However, the intricacy deepens. As light traverses the expanding universe, it undergoes stretching, a phenomenon termed redshift. Similar to how the pitch of an ambulance siren lowers as it recedes, the wavelength of light elongates when its source moves away. Given that space itself is expanding, almost all distant galaxies are withdrawing from us, and the light they emit is consequently stretched into longer, redder wavelengths during its journey, thus earning the designation redshift. Through quantifying the redshift in galactic light, astronomers can ascertain its distance and, more critically, the duration of that light's voyage. A significant redshift indicates an extremely remote galaxy and provides a profoundly ancient glimpse into the universe's infancy. This redshifted light contains vital information regarding the cosmos's structure, age, and chronology. It reveals the universe's expansion rate, galactic evolutionary processes, and even alludes to enigmatic forces like dark energy that govern everything on a monumental scale. Each spectrally shifted photon acts as a miniature messenger from the past, conveying encoded narratives of its origin and the universe's state at that time. Let's now consider telescopes, our instruments for temporal cosmic exploration. When viewing through a telescope, one not only gains greater clarity, but also perceives objects further back in time. A personal backyard telescope might reveal Jupiter's cloud formations from approximately 40 minutes prior. A more advanced observatory could present a galaxy as it appeared 500 million years in the past, a period when terrestrial life was still developing fins and gills. Then, there are the monumental instruments, grand observatories such as Hubble, James Webb, and their anticipated successors. These devices can gaze so profoundly into space, and consequently so far into the past, that they detect the faint luminescence of the very first galaxies to materialize. We are referring to cosmic entities that commenced formation merely a few 100 million years subsequent to the Big Bang. There's a subtle irony. In our pursuit to comprehend the universe's future, we largely dedicate ourselves to scrutinizing its past. Such is the inherent characteristic of light. It travels swiftly, yet not instantaneously. And owing to the universe's immense scale, even light must exert considerable effort to traverse it. Consequently, the universe, as perceived by us, is perpetually slightly outdated. It resembles observing a film still under production, with scenes appearing individually and non-sequentially, some from nearby galaxies and others from the farthest cosmic depths. Nevertheless, this delay is a profound advantage. Absent it, we would be incapable of reconstructing the narrative of creation. The staggered arrival of archaic light permits us to simultaneously witness disparate stages of cosmic evolution, akin to scattered pages of a novel across the sky. The outcome is a magnificent mosaic of time. In one vista, we might observe a relatively proximate, recently formed galaxy. In another, a faint light from billions of years past, when stars were coalescing from primordial gas clouds. All these perceptions are stratified, not merely spatially, but temporally as well. one might assert that we inhabit a museum constructed entirely of light. However, rather than perambulating between exhibits, we allow the photons to journey to us, traversing immeasurable distances to recount their tales, to inundate our skies with antique tidings from the genesis of all. There is an understated poetry in the notion that each upward glance is a gaze into a time machine, that the light caressing your eyes may have commenced its odyssey before Earth's inaugural tree, before the first cell, before the initial atmospheric breath. And all of this, these profound insights, emerge simply from interpreting light. By analyzing its hues, its displacements, and its antiquity, we decipher a silent idiom articulated across billions of years, a language that not only depicts the universe, but is the universe, encoded in movement and remembrance. The next occasion you observe a star twinkling overhead, recall that your perception is not of its current state. You are witnessing a rendition of it preserved in time, a historical shimmer still traversing the darkness. You are observing the universe as it appeared when younger, more compact, perhaps even more serene. And through the scientific lens, aided patiently by light, we progressively assemble our cosmic origin story, one remote luminescence at a time. Envision yourself in an early morning field, the grass dewy, the air crisp, a soft mist gently veiling the horizon. Your sight extends only a short distance, perhaps a few trees, the faint contours of a remote hill, before everything dissolves into a hazy indistinctness. You understand the world persists beyond the fog, yet your vision cannot penetrate it. In essence, this mirrors our experience within the universe. Regardless of how potent our telescopes grow, there remains a fundamental limit to our observational reach. This constraint arises not from conventional fog, but from the interplay of time, distance, and the distinctive character of the expanding cosmos. These limitations are termed cosmic horizons, and they delineate the boundaries of our observable universe. Now, diverging from Earth-distinct sky meets land horizon, cosmic horizons manifest in several forms, each possessing unique principles and import. The initial type is the particle horizon. Conceive of it as the utmost distance from which light, or any signal, could have reached us since the universe's genesis. It denotes the outermost boundary of the observable universe, the absolute confine of our present cosmic sphere. The particle horizon is fundamentally shaped by time itself, as the universe has endured for approximately 13.8 billion years. And given space's continuous expansion throughout that period, the maximum distance light could have traversed to arrive at our location today is approximately 46 billion light-years in any direction. This accounts for the observable universe's approximate 93 billion light-year diameter. It is the comprehensive perimeter of all we are presently capable of detecting. However, do not conflate this horizon with a physical barrier. There exists no demarcation, no luminous edge bearing a no-entry placard. Rather, it represents a limitation intrinsically integrated into the very essence of time. It's akin to standing on the shoreline of an immense ocean. You can gaze as far as the light permits, but you will never perceive beyond that subtle curvature, not due to an absence of matter, but because the signals have not yet had sufficient time to manifest. Subsequently, we address the universe's event horizon, distinct from the dramatic variety associated with black holes. In cosmological terms, the event horizon signifies the boundary past which no event can ever exert an influence upon us, regardless of the waiting period. It functions as the ultimate cosmic demarcation. Any region beyond this point is receding from us at a velocity exceeding the speed of light, attributable to spatial expansion. Consequently, light originating from there, however tenacious or enduring, will never overtake us. This is somewhat analogous to attempting to dispatch a message to a friend on a raft carried swiftly downstream by a river current. You cast a bottled note, but the current's force is such that the raft outpaces the bottle's ability to reach it. Despite your efforts, the message will remain undelivered. Such is the event horizon, where even light itself finds communication impossible. Currently, the cosmic event horizon is estimated to be approximately 16 billion light-years distant. This implies that certain cosmic regions are presently visible to us. However, should those regions emit fresh light today, that light will eternally fail to reach us. We are, in a profound sense, witnessing galaxies that are gradually receding beyond our grasp, discernible today, yet fated to vanish from our perception permanently. Lastly, we encounter the cosmological horizon, a term occasionally used synonymously with the particle horizon, but also applicable to broader space-time boundaries. This concept unifies these observational limits, underscoring that horizons extend beyond mere visual phenomena. They are intricately interwoven with the fundamental physics of the universe. The cosmological horizon can be conceptualized as the moving boundary of our visible cosmos. The observable universe constantly expands, allowing light from increasingly distant celestial bodies to eventually reach us. These cosmic horizons are dynamic and ever-changing. With the universe's advancing age, the particle horizon widens, granting more light time to arrive. However, due to dark energy and the accelerating expansion of space, the event horizon effectively shrinks in significance, pushing more galaxies beyond our ultimate reach. The cosmos increasingly becomes a realm of isolation, not because it's empty, but because the light from its far-flung regions struggles to keep pace. To visualize this, imagine the universe as a gradually inflating balloon, where dots on its surface drift apart, and the greater their initial separation, the faster they recede. We can only perceive the dots whose light has had sufficient time to travel to us. Beyond that threshold, light stretches and dims until it dissolves into the ever-expanding void. There's a profound, yet serene quality to these cosmic limitations. It's a gentle reminder that we are not all-seeing observers. Our perception is sculpted by cosmic history, the duration of light's journey, and the peculiar characteristics of the space it traverses. We are peering through a window that, though immense, is undeniably finite. Certain cosmic regions will forever remain enigmatic, regardless of our patience or ingenuity, not for lack of technology, but due to the intrinsic nature of space-time itself. These concealed domains aren't merely hidden behind a curtain, waiting to be drawn back. They exist beyond the reach of information, eternally unknowable. And yet, within these very confines, we have amassed incredible knowledge. We've charted galaxies, measured background radiation, and identified the echoes of the Big Bang. We've utilized the nebulousness of the particle horizon to comprehend the universe's structure and the radiance of ancient light to reconstruct its narrative. The horizons don't constrain our imagination. They define it. Much like the rising sun dispelling morning fog, each new discovery incrementally pushes back the mist, unveiling more of the cosmic panorama. Still, some segments will perpetually remain obscured beyond the curve, beyond the stretching, swelling demarcation where light will never arrive. Nonetheless, here we are, silently orbiting in a corner of the universe, observing photons that departed billions of years ago, deciphering their encoded messages, and contemplating what lies beyond the next subtle bend in the cosmic pathway. Even if we cannot behold everything, even if parts of the universe are permanently beyond our grasp, the beauty resides in the endeavor itself, in heeding the gentle hum of light, in pursuing it to the frontiers of knowledge, and in recognizing that while we may never witness the complete picture, we are nonetheless an integral part of the story. Not so long ago, in the vast timeline of human curiosity, prevailing wisdom held that the universe was largely static. Galaxies were in place, stars shone, and everything remained essentially fixed, a tranquil, everlasting cosmos. However, in the early 20th century, a pivotal revelation quietly emerged from a mountaintop observatory, and the universe has been in constant motion ever since. It was Edwin Hubble, whose name graces the renowned space telescope, who first detected an unusual phenomenon. While examining distant galaxies, he noticed their light was consistently redshifted, indicating that these galaxies were receding from us. Furthermore, the more distant they were, the faster they appeared to withdraw. This was not a random occurrence or a cosmic fluke. It was a consistent pattern, a fundamental law. Space itself, it seemed, was expanding. Now, this isn't quite the same as galaxies hurtling through a fixed, unchanging space like cosmic race cars. It's not as if they are exploding outwards into a pre-existing void. What's actually happening is more peculiar and elegant. Space itself is growing. Imagine space as the expanding medium and galaxies being carried along within it, much like raisins embedded in a rising loaf of bread. This analogy of raisin bread provides a gentle and surprisingly accurate depiction. Consider the dough as space and the raisins as galaxies. As the dough bakes and expands, it stretches in every direction. Each raisin finds itself farther from the others, not because it's actively moving on its own, but because the dough between them is expanding. There's no central raisin, no privileged direction, just a uniformly growing loaf. This is how the universe operates on a grand scale. Galaxies aren't rushing outwards through space like cannonballs. They are being carried away from each other as the very fabric of space stretches. That's why, regardless of your location in the universe, it appears as though everything else is moving away from you. From the perspective of any galaxy, space is expanding in all directions. It's somewhat akin to being inside a rising soufflé. No matter which bubble you occupy, all the other bubbles seem to drift away. The universe isn't expanding into anything. It's simply expanding. There's no outer shell, no boundary it's racing towards. Instead, the distances between unbound objects merely increase over time, as if the cosmic measuring tape is gradually lengthening. This concept of an expanding universe was so revolutionary when Hubble proposed it, that even Albert Einstein had to re-examine his own equations. Initially, Einstein had incorporated something called the cosmological constant into his general theory of relativity to ensure a static universe. He believed the cosmos had to be unchanging, and his equations, left to their own devices, suggested otherwise. Upon learning of Hubble's discoveries, he famously referred to the addition of the constant as his greatest blunder, though ironically, the concept has since been resurrected in explanations for dark energy. The universe, it seems, possesses a sense of humor. But returning to the expansion, one of the most beautiful consequences of Hubble's revelation is that it enabled us to rewind the cosmic clock. If galaxies are currently moving apart, they must have been much closer together in the past. This led scientists to the idea of a hot, dense genesis for the universe, which we now call the Big Bang. The term Big Bang can be somewhat misleading. It wasn't an explosion in space, like fireworks detonating in a dark field. It was more like the rapid swelling of space itself, occurring everywhere simultaneously. There was no center, no blast radius, just the entire universe suddenly stretching from a state of extreme density and heat. You cannot point to a specific spot in the sky and declare, "Ah, that's where the Big Bang occurred," because it happened everywhere, including precisely where you are now. That expansion persists today, nearly 14 billion years later. Galaxies continue to separate, and the light they emit continues to stretch along with them. The farther away an object is, the more its light is redshifted by the expanding universe, a cosmic stretching of time and space that influences every observation we make. Interestingly, the universe's expansion doesn't affect everything uniformly. It operates on the grand scale between galaxies and galaxy clusters, but it doesn't pull your morning coffee farther from your lips or separate the atoms in your chair. This is because gravity and other fundamental forces dominate on smaller scales, keeping things cohesively bound. The Milky Way isn't expanding. Your neighborhood certainly isn't expanding. And unless your washing machine is once again devouring socks, even your laundry pile remains relatively stable. Yet, on the cosmic scale, the expansion continues, and what's more, it's accelerating. This discovery, made in the late 1990s, came as a surprise. Scientists had presumed that the expansion might be decelerating due to gravity. Instead, they found that some mysterious force, now known as dark energy, is causing it to speed up. The cosmic dough isn't just rising. It's rising faster and faster with each passing moment. No one is entirely certain what dark energy is. It might be an intrinsic property of space itself, or a field we have yet to comprehend. But whatever its nature, it now dominates the universe's energy budget. That gentle stretch is evolving into a cosmic sprint, with galaxies receding from one another at ever-increasing velocities. There's a quiet poetry to it. The universe began with everything concentrated, dense, and unified. Over time, it expanded, cooled, formed stars and planets, and all the ingredients for life. And now, it continues its outward drift, stars aging, galaxies moving apart, space stretching into the unknown, like a story that commences with a bang, blossoms into intricacy, and then drifts into a gentle, infinite epilogue. There is no sound in space, but if there were, perhaps it would be the soft creak of rising dough, the occasional pop of a bubble, the slow shift of warm expansion. Not a violent cacophony, not a shout, but simply the peaceful hum of a universe unfolding into itself. So when we speak of the universe expanding, we're not describing objects flying away from some central point. We're referring to the very fabric of reality stretching, as calmly and steadily as a loaf of bread in an oven. It stands as one of science's most profound discoveries, and paradoxically, one of its most comforting. The notion that change can be slow, constant, and beautiful. And as we sit here, encircled by stars and bathed in ancient light, we are participants in that expansion. Every breath, every heartbeat, every thought you've ever had has occurred on a tiny rock, spiraling within rising cosmic dough. It's enough to ignite a hunger for answers, or at the very least, for a midnight snack. In physics, there's an inviolable rule. Nothing can travel faster than light. Not a spacecraft, not a signal, not even your cousin Greg, who claims to have once outrun traffic across 6 lanes in record time. According to Einstein's theory of relativity, the speed of light, approximately 299 million meters per second, is the universal speed limit, and no object with mass can ever attain or exceed it. Yet, in the vast cosmic expanse, astronomers have observed phenomena that appear to defy this principle. Galaxies seemingly moving away from us faster than the speed of light. Entire clusters of stars and dust slipping beyond our grasp at superluminal velocities. It sounds like a situation that should send physics into a panic. But rest assured, all is well. The universe isn't breaking its own rules. It's merely playing a very clever game with them. To grasp what's occurring, we must revisit a fundamental concept. Galaxies are not flying through space like comets in a vacuum. Instead, space itself is expanding, and galaxies are simply carried along with it. Visualize space as a rubber sheet with dots drawn on it. If you stretch the sheet, the dots move farther apart, not because they are crawling across the surface, but because the surface itself is growing beneath them. This is precisely how galaxies can appear to recede from each other faster than light. It's not that they are violating the speed limit. It's that the space between them is stretching so rapidly that the total separation increases at a rate greater than light can traverse. The galaxies themselves remain obedient citizens of physics. It's space that's performing the heavy lifting. Here's another helpful way to picture it. Imagine you're on a treadmill that's progressively speeding up. You attempt to walk towards someone at the opposite end, but the treadmill is moving backward faster than you can walk forward. Eventually, no matter how diligently you try, the distance between you and the other person continues to grow. It's not that you're walking too slowly, it's that the ground beneath you is counteracting your movement. In the universe's case, light is striving to travel through expanding space, but in some regions, particularly those very far away, space is expanding so quickly that the light makes no net progress towards us. It's like attempting to paddle a canoe upstream during a flash flood. The water flows too rapidly, and your boat is swept farther away despite your best efforts. This doesn't violate relativity because that theory only prohibits objects from moving through space faster than light. It makes no stipulations about how far space itself is permitted to expand. And it turns out, space has quite a flair for dramatic growth. Consider, for instance, a period called cosmic inflation. This was an astonishingly brief moment just after the Big Bang, when the universe expanded at an absolutely staggering rate, vastly exceeding the speed of light. In less than a trillionth of a second, the universe grew from something smaller than a proton to something the size of a grapefruit, or possibly even larger. Try explaining that expansion in a recipe. And once again, this faster-than-light swelling broke no rules. It was space itself undergoing expansion, not particles racing through it. It's one of the rare instances in physics when faster-than-light travel is not only permissible, but actively encouraged. Just don't attempt it in a spaceship. Your engines will not appreciate the suggestion. This rapid inflation smoothed out the early universe, ironing away wrinkles and irregularities like a cosmic steam press. It also helps explain why the universe appears so uniform in every direction, despite the fact that distant regions haven't had time to exchange information. Inflation spread everything out so swiftly that local differences became subtle and vastly separated. Even now, billions of years later, we are still observing the effects of that expansion. Space continues to grow, carrying distant galaxies farther and farther away from us. Some of those galaxies are now receding faster than light, not because they are accelerating, but because the space between us is expanding faster than light can close the gap. This implies that there are regions of the universe we can never see. No matter how long we wait, their light will never reach us. And if they emitted new light today, that light would be swept away into the ever-deepening void. These galaxies aren't lost because they're moving too quickly. They're lost because the path between us is stretching out faster than their signals can travel. It's somewhat like attempting to send a postcard across a river where the opposite bank is drifting away faster than you can throw. Regardless of how many stamps you affix, the postcard will never make it. Eventually, even the concept of delivery becomes meaningless. So when astronomers state that some galaxies are receding faster than light, what they mean is this: due to the expansion of space, the separation between us and those galaxies is increasing at a rate greater than light can maintain. There's no violation, no rebellious physics, just a clever interpretation of how space and time can flex in ways our instincts don't always grasp. In fact, this cosmic phenomenon has another peculiar consequence. There are galaxies we can observe today, clearly through our most advanced telescopes, that have already crossed this horizon. They remain visible because the light they emitted long ago is still arriving. However, their newer light, generated presently, is already beyond our reach. It will never arrive, not even if we await an eternity. It's a bit like watching the taillights of a car that has just rounded a corner. You can still perceive the glow, but the car itself has already vanished, cruising down a road you will never follow. That light is a phantom, a message from a past that can no longer be updated. This reality carries a certain peaceful melancholy. The universe is brimming with narratives we'll never hear, stars we'll never behold, galaxies we'll never know existed, not because we didn't search diligently enough, but because the cosmos itself is drawing the curtain, stretching the stage beyond our perception. Yet, this too is part of the marvel. The fact that we've managed to glimpse so much of the universe's past is nothing short of miraculous. Despite all the immense distances and distortions, we've still observed billions of light years in every direction. We've intercepted ancient photons mid-flight, reconstructed the origins of galaxies, and even traced the faint afterglow of the Big Bang itself. And all of this has occurred from a tiny planet orbiting an unremarkable star in an average galaxy within a universe where space expands faster than light. It's enough to make one feel small, but also strangely fortunate. Because here we are, attuned to the whispers of an expanding cosmos, watching light striving to reach us, counting galaxies as they recede into the distance. And all the while, the cosmic dough continues to rise, carrying with it the aspirations of curious beings who once pondered just how far light could travel. When we contemplate the universe, it's tempting to envision it as a vast black box, a huge rectangular expanse with a top, bottom, left, right, front, and back, simply floating in some void. Perhaps it has edges. Perhaps it extends infinitely. Maybe there's a colossal cosmic wall bearing a "Do Not Enter" sign and a thoroughly bored security guard. But the true geometry of space is far more subtle and profoundly more captivating. It turns out that space isn't necessarily flat like a tabletop. It might be curved. In fact, it could possess positive or negative curvature, or merely be ever so gently flat. And this isn't solely a matter of aesthetics. The geometry of the universe holds deep implications for its evolution, its behavior, and whether it might eventually curve back in on itself or continue stretching outwards forever. Let's explore the three primary possibilities. The first is a flat universe, akin to an infinite sheet of paper. In this model, the rules of geometry operate precisely as we learn them in school. Parallel lines never intersect. Triangles always sum to 180 degrees. And if you journey in a straight line, you'll never loop back. You'll simply continue indefinitely through an endless cosmic plane. The second option is a closed universe, shaped like a sphere, or more accurately, the three-dimensional equivalent of a sphere. Here, space curves back upon itself. If you were to embark in a straight line in any direction, somehow avoiding stars, planets, and all other cosmic debris, you would eventually return to your starting point. It's like walking in a straight line around the surface of the Earth. You wouldn't fall off, you just keep circling. Though it might demand several billion years and an exceptionally durable pair of shoes. The third possibility is an open universe, shaped like a saddle. This space curves outwards, much like a Pringle chip. In this geometry, parallel lines eventually diverge. Triangles sum to less than 180 degrees, and if you attempted to circumnavigate the universe, you'd never return to your origin. You'd simply drift farther and farther out into the cosmic immensity. These shapes, flat, closed, and open, are not merely abstract concepts. They are directly linked to the universe's overall density and energy content. Specifically, how much matter and energy exist compared to what would be required to perfectly balance the universe. This critical density determines whether space bends inward, outward, or remains uncurved. If the actual density surpasses the critical density, space is closed and positively curved. If the density is less, it's open and negatively curved. And if the densities align just right, the universe is flat. It's somewhat like the Goldilocks principle of cosmology. Not too much, not too little, but just enough to maintain a straight geometry. And how do we measure this? As it happens, the universe leaves clues in the cosmic microwave background, CMB, the ancient light that has been traveling since shortly after the Big Bang. By analyzing the minute fluctuations in this faint glow, scientists can ascertain how space bends light over vast distances. It's akin to using the pattern of ripples on a pond to deduce the shape of its shore. So far, the evidence suggests something remarkable. Our universe appears to be extremely close to flat. Perhaps not perfectly flat, but close enough that any curvature is too minuscule to detect with current instruments. It's like standing on an enormous plane that might have a slight bend somewhere beyond the horizon. But as far as you can see, it appears quite straight. Now, this is where things become truly intriguing. A flat universe can still be infinite or finite, and a closed universe, surprisingly, can be finite but unbounded. That phrase initially sounds contradictory, like saying you have a mug that's full but contains no coffee. But it makes sense with a little consideration. Take the surface of a sphere. It's finite. You can measure its total area. Yet, it has no edges. You can walk around the surface of a globe indefinitely and never fall off, because there is no edge. The entire surface connects back on itself. Now, extrapolate that concept to a three-dimensional version. That is what cosmologists mean by a space that is finite but unbounded. It's a closed loop, a self-contained bubble of geometry. This type of space lacks a border. There's no place where the universe ends and something else begins. It's simply space curving back around in a grand, subtle loop. And because we exist within it, we would never directly perceive it. We would simply continue drifting forward, believing we're moving in a straight line, while subtly bending back towards our origin. Even in a flat or open universe, infinity introduces its own peculiar characteristics. An infinite universe implies an endless number of galaxies, stars, and potentially even repeating patterns. Somewhere out there, if the universe is truly infinite, there could be another version of you listening to this same content, possibly in a slightly different set of pajamas. It's important to note that we can only observe a small fraction of the universe, beyond which lies our observable horizon. We don't definitively know how space behaves beyond that. It could be flat indefinitely, or it could curl into a loop too vast for us to detect. The curvature might be so slight that even a light beam traveling for billions of years wouldn't reveal it. It's like trying to discern whether the Earth is round while standing in a meadow. You don't perceive the curve, but it is undoubtedly there. Cosmic geometry also influences the ultimate fate of the universe. In a closed universe, gravity might eventually slow the expansion and cause everything to contract, leading to a big crunch. In an open or flat universe, expansion could persist indefinitely, thinning out matter and cooling the cosmos into a gentle fade. Although, with dark energy accelerating things apart ever faster, a big crunch seems improbable, at least based on our current understanding. What's particularly comforting, in a quiet way, is that regardless of its shape, we are an intrinsic part of it. Whether the universe loops or drifts, curves or stretches, we are woven into its very structure. Our atoms conform to its geometry. Our light traces its curves. Our thoughts echo through its vast halls. We don't just exist in space, we are space, folded into itself in a dance of mass and motion. So if the universe is flat, we inhabit a grand plane of cosmic possibility. If it's curved like a sphere, we might be looping within an invisible bubble. If it's open, we're surfing an endless saddle, venturing into infinity with no planned return journey. Whichever version holds true, it is strange, elegant, and beautiful, perfectly bewildering in just the right proportion, and that's precisely where its allure lies. You don't need to precisely define the geometry of space to appreciate its profound mystery. You can simply look upward, smile at the distant stars, and grasp that you occupy a minuscule portion of something vast and enigmatic, a cosmos whose configuration we are still striving to comprehend from an internal perspective. Picture yourself as a minuscule inhabitant on the surface of a balloon. You're able to move in any cardinal direction across its exterior, but you cannot delve beneath it or ascend above it. Your entire existence is confined to that two-dimensional skin, which is curved yet seamless. You're unaware that a gigantic cosmic child with a helium tank is holding the balloon. You only know that if you walk in a straight line, you will eventually return to your starting point. This illustrates the fascinating nature of curved space. It operates under principles that don't always align with our daily experiences. Yet, it becomes perfectly logical once you attune yourself to its rhythm. And while we humans exist in three spatial dimensions, two-dimensional curved surfaces offer an unexpectedly useful way to conceptualize what our universe might be doing on a far grander scale. Let's begin with a straightforward example. On a flat plane, such as a sheet of paper or a still tabletop, geometry behaves predictably. If you draw a triangle, its angles will invariably sum to 180 degrees. If you sketch two parallel lines, they will never intersect. And if you begin walking in a straight direction, you'll continue indefinitely unless you encounter an obstruction or an unfortunate coffee spill. Now, envision walking on the surface of a sphere, perhaps a planet or the aforementioned balloon. Geometry begins to exhibit peculiar characteristics. If you construct a triangle using great circles, like the equator, and lines of longitude, the sum of its angles can exceed 180 degrees. Parallel lines don't maintain their parallelism for long. They converge at the poles or diverge, depending on their trajectory. Crucially, if you walk in a straight path on this curved surface, you will eventually arrive back at your origin without ever having turned around. No boundaries, no edges, just a continuous circuit, From your limited vantage point on the surface, the space around you appears infinite, but in reality, it is finite and wraps back upon itself. Now, take that concept and amplify it. Imagine our entire universe as a three-dimensional version of that balloon's surface, except instead of curving in 2 dimensions, it curves in 3, or rather, in a manner we cannot easily visualize because it bends within higher dimensional space. You and I exist within this 3-dimensional space, navigating through it without ever perceiving an outside. Much like the balloon creature never sees the air surrounding the balloon. In this analogy, galaxies are akin to dots inscribed on the balloon's surface. As the balloon inflates, these dots drift further apart. This isn't because they are actively migrating across the surface, but because the surface itself is expanding. This is what cosmologists mean when they state the universe is expanding. It's not that galaxies are hurtling through space like comets on a journey. It's that space itself is growing, carrying the galaxies along with it. And just like our small balloon inhabitant, if the universe is indeed curved and finite, then traversing a straight line for a sufficiently long period might ultimately bring you right back to your starting point. You wouldn't tumble off the edge of space because no such edge exists. The loop closes smoothly. It is a finite space without a boundary, a notion both strange and delightful. You could embark on an endless voyage through a finite universe, never encountering a wall, never exhausting the available room. The balloon analogy also helps us comprehend another aspect, why there is no distinct center to the universe. Just as there is no single central point on a balloon's surface, the universe lacks a singular origin from which everything is expanding. The expansion occurs uniformly everywhere. Every point on the balloon moves away from every other point as it inflates. You could choose any location and designate it as here, and the panorama would appear identical in all directions. It's important to pause here and acknowledge that the balloon analogy isn't flawless. It serves merely as a model to assist our 3-dimensional minds in grasping a higher dimensional concept. The balloon's surface is 2-dimensional and embedded within 3-dimensional space, which we can readily observe and picture. But if our universe is curved, it might be curving within a higher dimensional space that we cannot directly perceive. It's not floating within a larger container. Space doesn't require an external outside to curve. It can curve intrinsically, based on its own inherent properties, without any external reference. This concept of intrinsic curvature represents one of the profound insights of Einstein's theory of general relativity. Space, and space-time more broadly, is not a passive backdrop. It possesses shape and structure, and that shape can evolve over time. Mass and energy dictate how space-time curves, and the curvature of space-time in turn dictates how matter moves. It's an elegantly reciprocal relationship, one that governs everything from planetary orbits to the behavior of galaxies on the grandest scales. The curvature of space also influences the trajectory of light. In curved space, light doesn't follow what we typically consider straight lines. Instead, it traces the shortest available path, known as a geodesic. On a sphere, this is a great circle. In our universe, it's a curved trajectory that bends under the influence of gravity and the very shape of space. This is why massive objects like stars and black holes can deflect light, a phenomenon termed gravitational lensing. So, when we gaze at the night sky, we aren't merely observing objects scattered through flat, empty space. We are witnessing a network of light-traversing curved space, stretched, bent, and molded by the mass of everything surrounding it. It's akin to viewing the stars through a slowly shifting funhouse mirror, except the distortions convey a genuine truth about the cosmos's form. Now, let's revisit our balloon one final time. As it inflates, the distances between the galaxies on its surface increase. However, the galaxies themselves do not expand. They retain their original size. This is because the expansion of space occurs on vast scales, specifically between objects that are not gravitationally bound to one another. So, our Milky Way galaxy, our solar system, even our planet, and its well-worn coffee shops, none of these are being stretched like taffy. The expansion only asserts itself in the immense voids between galaxies. And what propels this expansion? Well, current understanding suggests that dark energy, a mysterious form of energy intrinsic to space itself, is causing the universe to accelerate its growth. It's as if the balloon isn't just inflating, but doing so with increasing speed with each breath. We don't precisely know what dark energy is, but we can discern its effects in the movement of distant galaxies and the dispersal of ancient light across the cosmos. So, what does this imply for us? It means we inhabit a space that might be curved, potentially finite yet boundless, expanding yet without a center, shaped by principles that defy our everyday comprehension, yet are perfectly logical within the grand cosmic ballet. And all of this, the curves, the expansion, the potential to loop back to our origin, can be conceptualized using a simple balloon, a pliable metaphor drifting through our thoughts, whispering age-old secrets about a universe that expands not outward from a central point, but intrinsically within itself. The next time you observe a balloon ascending into the sky, offer it a brief acknowledgement. It may be filled with helium and bring simple joy, but it also embodies the form of something far more profound, a gentle curve, an expanse of space, and the quiet realization that perhaps, just perhaps, the destination you're heading toward is also where you began. Only now you will have journeyed through the universe to reach it. Infinity. The very word feels as though it should resonate when spoken. It is immense, enigmatic, and more than a little daunting. It conjures images of ceaseless stars, boundless expanses, and mathematical problems that prompt high school students to re-evaluate their career aspirations. But what does it truly signify when we ask, is the universe infinite? Is space genuinely unending, extending forever without a conclusive border or barrier? Or is there a more subtle reality at play? Let's begin with what we know. Thus far, all our measurements concerning the large-scale architecture of the universe indicate that it might be infinite. Observations of the cosmic microwave background, the faint residual glow from the Big Bang, reveal that space is remarkably close to being geometrically flat, not lumpy like a sphere and not saddle-shaped, but flat in a geometrical sense. And within the framework of general relativity, a flat universe could indeed be infinite. If it is not, it is at the very least vastly, vastly larger than the portion we can observe. This brings us to the observable universe, the cosmic sphere within our view. It spans approximately 93 billion light-years across. This represents the segment of the universe we can access, because light from those regions has had sufficient time to reach us since the cosmos's inception. But beyond that, it could continue indefinitely. There might be innumerable galaxies, cosmic structures we will never detect, entire regions of space perpetually beyond our perception. And here's the crucial point. We cannot definitively prove or disprove the universe's infinitude because we are limited by our observational capabilities. We are like ants on a beach, looking in every direction and perceiving only sand. For all we know, the beach extends across an entire continent. Or perhaps it terminates a few dunes away in a tidal pool teeming with curious crabs. We simply cannot see far enough to ascertain. This highlights an important distinction. We do not measure infinity in the same way we measure, for instance, the distance to the moon. You cannot affix a ruler to space and continue measuring until the numbers run out. Infinity is not a numerical value. It is an abstract concept. And in science, concepts necessitate empirical evidence. This is where it becomes challenging. You can never directly witness infinity. You can only search for indicators that space exhibits no signs of curving back on itself, ending abruptly, or behaving in a manner that suggests it loops. So far, we have scanned in all directions and detected no discernible edge, no sudden termination, no cosmic barrier displaying a do not pass sign. But that does not preclude its existence. It merely signifies that it lies beyond our current visual range. And unless we suddenly invent a telescope capable of exceeding the speed of light and outpacing the universe's expansion, that situation is unlikely to change anytime soon. The notion of an infinite universe carries with it some profoundly peculiar implications. If space is truly boundless, then the quantity of matter it contains is also likely infinite, or at least so astonishingly immense that it functions as such. This implies an unending multitude of stars, planets, comets, dust clouds, and indeed, potentially even life. Somewhere within the furthest reaches of an eternal cosmos, there might exist another planet identical to Earth. Perhaps it possesses trees that grow horizontally, or oceans that shimmer with unusual hues. Perhaps it harbors beings asking the same fundamental questions we are, pondering whether their universe ever concludes. And here's where it begins to challenge conventional thought processes. In an infinite universe, if matter is distributed more or less evenly, then the principles of probability suggest that patterns will eventually repeat. This means that somewhere out there could be a version of you, or several. Some might be almost perfectly identical. Others might have opted for a different breakfast cereal this morning and inadvertently altered the trajectory of their entire day. Now, rest assured, this is not intended to be disconcerting. You are highly unlikely to encounter your cosmic doppelganger at the local supermarket. These regions are likely so incredibly distant that they are forever inaccessible. The light from those parts of space will never, ever reach us, even if we were to wait for a duration exceeding the age of the universe multiplied by every grain of sand on Earth. Nevertheless, the ramifications are profound. Infinity isn't merely a matter of scale. It represents a fundamental shift in perspective. It transforms the universe from something merely large into something truly boundless. You no longer need to ponder what lies beyond the edge of the map, because there is no edge, only more map, ceaselessly. Of course, there are sound scientific grounds for exercising caution when assuming the universe is infinite. We possess only a finite sample to work with, and cosmologists remain open to the possibility that space could be extraordinarily vast, yet still finite. It might curve subtly back upon itself in a way we cannot yet detect, looping through higher dimensions or forming a shape more exotic than anything we have ever conceived. There is also the question of time. The universe might be infinite in spatial extent, but finite in duration. It had a beginning, which we refer to as the Big Bang, and while the concept of a beginning is itself intricate, it suggests that even if the cosmos is spatially endless, it has not perpetually existed in its current configuration. Philosophically, infinity challenges the manner in which we relate to the universe. Most elements in our daily lives possess limits. our time, our energy, the quantity of cookies in the jar. Infinity shatters that paradigm. It eradicates boundaries and unveils a realm of endless possibilities that can be simultaneously inspiring and overwhelming. Some ancient thinkers harbored deep apprehension regarding the idea of infinity. Aristotle, for example, maintained that the universe must be finite because actual infinities were simply too bizarre to accept. And even today, some scientists and philosophers debate whether true infinities can exist in the physical world, or if they are merely useful abstractions. But regardless of whether the universe is infinite or not, contemplating it holds immense value. It expands the mind, fosters humility, and reminds us of the profound limitation of our own perspective. When you gaze up at the stars, you are peering into a mystery so immense that even our most audacious measurements barely scratch its surface. You are perceiving only a localized radiance, a few lights in the window of the cosmic mansion. And yet, here we are, minuscule beings on a rotating planet, questioning the extent of space. We construct instruments to pursue ancient light. We devise mathematics to frame the inconceivable. And we lie awake at night pondering what lies beyond the last star we can perceive. Perhaps the universe is infinite. Perhaps it is not. Either way, it is more than sufficient. More than enough to fuel our inquiries, our narratives, our scientific endeavors, and our aspirations. More than enough to remind us that we are an integral part of something truly immense. And the most marvelous aspect of all is that you don't need to know its full extent to feel at home within it. You are already interwoven into its very fabric. A fleeting thought at the edge of the observable, glowing gently within a cosmos that may never cease. There's something inherently compelling about the idea of an edge. We grow up accustomed to edges, walls, fences, sidewalks, lunchboxes. Everything we encounter seems to have a definite stopping point. So when we contemplate the universe, it's only natural to envision that it too must conclude. Surely, after an almost unimaginable distance, space must reach its end, like the ultimate room in an enormous manor, or the border of a colossal tabletop suspended over an abyss. But here's the unexpected turn. Space doesn't actually require an edge. It can be finite in its extent without possessing any boundary whatsoever. And that's where things become wonderfully peculiar. Let's start with a simple illustration. Picture the Earth's surface. If you were to walk in a straight line in any direction, you would eventually loop back to your original position. You wouldn't plummet off anything. You wouldn't collide with a wall. And you wouldn't stumble upon a signpost proclaiming, "End of Earth, please turn around." The surface is finite but without bounds. It seamlessly wraps back upon itself. Now, extend that concept to a three-dimensional space. Imagine existing within a volume of space that encloses itself, much in the same way the surface of a globe does in 2 dimensions. If you could continuously move forward in a perfectly straight line through this space, you might ultimately return to your starting point, never having encountered a wall, a precipice, or any form of boundary. This kind of space is not speculative fiction. It is a perfectly legitimate model in cosmology. It is referred to as a finite, unbounded space. It sounds contradictory at first, like asserting that a cup can be full of tea yet contain no liquid. But once you grasp the underlying geometry, it makes perfect sense. Space can be configured in such a way that it closes in on itself, forming a complete volume without ever needing to terminate. One of the classic geometric forms used to exemplify this idea is the torus. Imagine a donut, not the kind filled with jelly, but the smooth, ring-shaped variety with a hole in the middle. The surface of the donut is two-dimensional. You can traverse its surface indefinitely without leaving it, yet it possesses no edges. It loops back on itself both horizontally and vertically. If you are an ant walking on the donut, you can continue forever without ever hitting a barrier. Now, visualize a three-dimensional analog of that, where space loops in multiple directions. This doesn't mean the universe is shaped like a baked good, but the torus helps us mentally picture how space might behave if it were finite and without borders. You could start at one point in space, journey in a straight line, and after an exceptionally long duration, find yourself precisely where you began, like a galactic boomerang. Another helpful comparison comes from video games. In certain classic arcade titles, such as Pac-Man or Asteroids, if your character exits the screen on one side, it instantly reappears on the opposite side. It's not that an invisible tunnel exists. They have simply looped around on a map that wraps back on itself. These are two-dimensional renditions of a toroidal space. The game world is finite in size, but its edges do not function like real-world walls. They connect. In theoretical cosmology, this concept is more than mere playful speculation. Some models propose that the universe could possess a topology, its fundamental shape, that subtly loops back. We might not perceive these loops unless we looked far enough, and in precisely the right direction. There has even been conjecture that if the universe is relatively small and curved just so, we might observe recurring patterns in the cosmic microwave background, akin to mirrored wallpaper left over from the Big Bang. Thus far, we have not discovered any definitive evidence of this repetition, but the idea has not been entirely discarded. The deeper truth is that the universe doesn't require an external surface or a surrounding void. That's a very human way of conceptualizing space, thinking of something contained within something else. But space isn't an object embedded in a larger object. It is the object. It's not like a balloon floating in the air. It's more like the entirety of the balloon itself, with all of us fixed to its surface, unable to step outside and observe it externally. Even if the universe is infinite, it still doesn't necessitate an edge. Infinity is not a location. It's a characteristic. Saying the universe is infinite is analogous to saying numbers never end. You don't need to locate the last number to understand that one doesn't exist. Similarly, you don't need to pinpoint the edge of space to know that there might not be one. Edges also introduce philosophical conundrums. If an edge existed, what would lie beyond it? More space? Something entirely different? A blank void existing uncomfortably, awaiting definition. The moment you introduce an edge, you create a paradox. If something exists beyond it, then space hasn't truly concluded. And if there's genuinely nothing, then how can it be said to exist at all? In contrast, a universe without edges completely bypasses this confusion. It simply is. You can continue moving indefinitely, or you might return full circle. There's no edge to fall from, no cosmic warning signals, and no need to define what lies beyond the beyond. This doesn't mean we will ever cease to inquire about boundaries. Our brains are predisposed to think in terms of containers. We prefer beginnings, middles, and ends. But the universe seems largely indifferent to our mental organizational systems. It stretches, curves, and potentially loops, all without presenting a clean border to mark a conclusion. Interestingly, even if space itself has no edges, time might. Our universe had a beginning, at least from our current perspective, with the Big Bang approximately 13.8 billion years ago. That's not a specific point in space. but a specific moment in time. A point when space itself commenced its expansion from an earlier state. Asking what existed before the Big Bang is like asking what lies north of the North Pole. It's not that the question is meaningless, it's that our usual coordinates cease to be applicable. All of this paints a portrait of a universe far more subtle and extraordinary than a colossal box. It's not an object you can simply open or peer around. It's more like a melody that plays itself forward, weaving through dimensions and humming through time with no ultimate note, no conclusive chord, just an endless progression. And within that melody, there are no rigid edges, only connections, undulations and continuations. Whether it loops or extends infinitely, the universe doesn't confine itself like a room. It expands like an idea, not constrained by walls, but shaped by relationships, gravity, light, motion, time. Therefore, if you've ever envisioned a spaceship bravely voyaging towards the universe's edge, picture this instead: a long, tranquil journey that never discovers a precipice, only more stars, more inquiries, and more space. Not necessarily because the universe continues indefinitely, but because it never possessed an edge to begin with. Before there were stars, before there were galaxies, even before atoms had properly settled into their roles, there was a luminosity. A gentle, uniform light diffused across the universe like a warm mist, extending in every direction. It wasn't a focused beam, a camera flash, or a grand pyrotechnic display. It was quieter, softer, like the initial rays of dawn filtering through a window before anyone has had a chance to open their eyes. And some of that light persists with us today. We refer to it as the cosmic microwave background, or CMB for short. It is not merely the oldest light we can perceive. It is the oldest light anyone can perceive. A faint echo from the earliest universe, still gently drifting through space, passing through galaxies, stars, planets, and occasionally, with the appropriate instruments, into our detectors. To grasp the origin of this light, let us journey back in time, far back, approximately 13.8 billion years ago. The universe originated in an extremely hot, dense state, a singularity of seething energy and unimaginable temperature. In its initial moments, space expanded rapidly, spreading out that energy like batter in a pan. As the universe grew, it cooled, not abruptly, but steadily, like a cosmic kettle gradually removed from a heat source. Initially, the universe was a blinding, opaque soup of particles and radiation. Photons, the fundamental particles of light, incessantly bounced around, trapped within a fog of charged particles. Electrons and protons whizzed about independently, and light could not travel far before being scattered in a new direction. Imagine attempting to shine a flashlight through a dense cloud. That accurately describes the universe during its first few 100,000 years. Initially murky, tumultuous, and highly active, yet a remarkable event unfolded. Approximately 380,000 years post-Big Bang, the cosmos had sufficiently cooled for protons and electrons to merge into electrically neutral hydrogen atoms. This pivotal point, known as recombination, fundamentally altered reality. With fewer charged particles present to scatter it, light could suddenly move unimpeded. The obscurity vanished. The universe became clear, and its inaugural light burst forth. This primordial radiance, unleashed across the cosmos, has been journeying ever since. It saturates the universe in every direction, attenuated over billions of years of cosmic growth. What was once an intense surge of ultraviolet energy has now mellowed to a faint microwave hum, a soft murmur rather than a loud blast. Still, it surrounds us, permeating your space right now like a delicate, unseen current from the dawn of existence. The CMB's initial detection occurred nearly by chance. During the 1960s, radio astronomers Arno Penzias and Robert Wilson utilized a substantial horn antenna for signal research. They consistently observed a persistent background interference regardless of where they aimed their antenna. They meticulously cleaned their gear, re-verified calculations, and even evicted pigeons from the apparatus, suspecting them as the cause. Nevertheless, the interference stayed constant, even, and oddly cosmic. What they had inadvertently encountered was the residual glow of the Big Bang. The cosmic microwave background, previously theorized and now empirically observed in its subtle grandeur. That faint static on their radio receiver proved to be a direct insight into the nascent universe. Subsequently, researchers have charted the CMB with remarkable precision. Missions such as COBE, WMAP, and the recent Planck satellite have furnished us with an incredibly detailed image of this primal luminescence. Their findings unveiled more than mere light. They presented a universal schematic, a portrayal of the cosmos from when it was under 500,000 years old. Initially, the CMB appears remarkably homogeneous, exhibiting consistent temperature and luminosity irrespective of observation direction. However, upon closer inspection, minor variations become visible. These are subtle warm and cool regions, differing by mere millionths of a degree. These minute undulations are not flaws. They are the genesis of all things, infinitesimal density disparities that, over eons, evolved into stars, galaxies, and ultimately you, engaging with a cosmic explanation while comfortably attired. These minor divergences serve as vital indicators. They inform us about matter distribution in the nascent universe, unveil the physics governing the cosmos at its inception, and permit us to evaluate hypotheses concerning the evolution of space and time in creation's earliest moments. The very geometry of the cosmos also imprints itself on the CMB. Should space be curved spherically, saddle-shaped, or entirely flat, these configurations would subtly alter light's passage. By analyzing the scale and distribution of CMB fluctuations, scientists can deduce the universe's vast architectural form. Thus far, available evidence suggests a flat universe, at least within our observational limits. This is comparable to deciphering a shoreline shape by observing patterns of ripples on a pond surface. The way these undulations expand and shift conveys details about their medium. Similarly, the CMB encrypts information regarding the universe's shape, dimensions, and constituents. It represents light as information, photons as chroniclers. There's a profound serenity in contemplating that radiance, a soft, diffuse wash of primordial light, neither glaring nor fiery, but composed and steady. It's not visible to the naked eye, yet it's perpetually present, akin to the universe's own enduring lullaby. With the appropriate radio receiver, one could perceive it ubiquitously, not as a melody, but as a subtle, warm static, an unceasing, faint presence intrinsically woven into the spatial fabric. It is the closest analogue to a baby picture for the universe, a record of its initial moment of lucidity. And it persists in murmuring to us, long after stars ignited, galaxies coalesced, and Earth commenced its orbit around the Sun. This light has outlasted stellar generations, traversed immeasurable gulfs, and arrived within your lifetime, poised to recount its narrative. Amidst a cosmos brimming with enigmas, the CMB offers something tangible, something measurable, mappable, and comprehensible. It underscores that understanding the universe's origins doesn't necessitate pursuing its farthest reaches. Sometimes, the revelations already envelop us, patiently awaiting discovery within that glow. Therefore, when you next gaze at the nocturnal sky, endeavor to envision it not as dark and void, but permeated by an ancient light too dim for sight. It has traveled for over 13 billion years, continually stretching, carrying the silent annals of everything. And even now, in the stillness of space, it persistently shines. Does the universe possess an actual edge, an ultimate limit, a cosmic veil, some definitive demarcation where space concludes? This inquiry frequently surfaces, not solely within speculative fiction, but within genuine scientific discourse, exchanged amidst blackboard equations and telescopic observations. Although conventional cosmology generally posits a universe devoid of any definitive boundary, certain speculative hypotheses and conceptual explorations invite consideration of more unusual scenarios, where limits might indeed exist, even if imperceptible to our senses. Let's begin with the notion that our three-dimensional cosmos might be a form of surface or brain suspended in a greater dimensional expanse. This concept is fundamental to brain-world cosmology, a branch of string theory. In this framework, our universe could be a vast three-dimensional membrane, or brain, residing within a bulk of higher dimensions. We are constrained to this brain. All known particles and forces, save gravity, are confined here, much like insects on a soap bubble. Gravity, being somewhat more adventurous, might permeate into the adjacent dimensions, which some physicists theorize explains its relative weakness compared to other forces. If this theory holds, our universe could possess an edge, not within our three-dimensional space, but within the higher dimensional bulk beyond our direct perception. One could visualize the brain having a perimeter or limit in these unexperienced dimensions. From our vantage point, everything appears boundless and uninterrupted. However, from the perspective of a hypothetical five-dimensional entity with superior sight, we might resemble a cosmic disk with boundaries along its periphery. The thought of being observed by a being with more dimensions than we can grasp is slightly disquieting, yet also reassuring. We, in turn, would be their perplexing enigma. Next, consider the concept of cosmic domain walls, frontiers between distinct spatial zones where the laws of physics could vary subtly. These walls are hypothesized by certain early universe symmetry-breaking theories. Envision space undergoing a phase transition, much like water freezing, but without uniformity. Some areas solidified under one set of principles, while others adopted a divergent course. The junctures between these disparate regions could establish domain walls, immense formations spanning the cosmos, delineating one cosmic environment from another. In most theoretical frameworks, these walls would have rapidly vanished or dissipated into insignificance, yet some speculative models suggest their continued existence, lingering in deep space like silent guardians. Traversing one might be unremarkable, or it could resemble entering a parallel reality with subtly altered chemical properties. Your atoms might exhibit minor behavioral differences, or your tea could inexplicably acquire a faint lemon flavor. Regarding transitions to alternative realms, some theorists have contemplated if our entire universe might literally reside within a bubble. Not symbolically, but actually. A spatial bubble generated during a period of cosmic inflation. Envision the primordial universe effervescing with quantum fluctuations. In specific locales, inflation ceases, and a spatial bubble emerges, possessing its distinct characteristics, including fundamental constants, gravitational strength, and the count of spatial dimensions. Each bubble constitutes a distinct universe. This phenomenon is occasionally termed eternal inflation, and it inherently points toward the concept of a multiverse, a vast froth of bubbles, each endowed with its unique physics. From this perspective, an implicit boundary exists, where our bubble universe interfaces with the inflationary continuum, or where it might eventually encounter another bubble. However, such collisions would be extraordinarily infrequent. If our universe is a bubble amidst an immense cosmic effervescence, our adjacent neighbors are too remote for any interaction, rendering our bubble's edge more conceptual than discernible. Nevertheless, there is a peculiar allure in conceiving the universe as an element of a teeming ocean of other realities, each expanding into the emptiness like suds in a basin. Furthermore, there is Gödel's rotating universe. Indeed, the same Gödel renowned for his incompleteness theorems in mathematics. In 1949, he devised a solution to Einstein's equations depicting a universe that rotates as a singular entity, not merely individual galaxies in motion, but the entire space-time fabric gradually spiraling like a colossal cosmic vortex. Within this peculiar model, time and space are so intricately curved that, hypothetically, one could traverse a particular trajectory and return to an earlier moment in time. Essentially, a temporal loop. Gödel's universe lacks spatial boundaries, but blurs the distinction between spatial limits and causal relationships, which is more perplexing. An ultimate barrier at the universe's end, or the capacity to encounter your past self. Before contemplating a journey to the past, it's crucial to acknowledge that Gödel's rotating universe contradicts observational evidence. Our cosmos does not exhibit such global rotation, and his envisioned time loops remain purely theoretical. However, the model possesses merit, not for its physical accuracy, but for its capacity to expand our intellectual horizons. It underscores that cosmic principles are dictated by mathematical equations, not human conjecture, and these equations occasionally permit realities more bizarre than fiction. A further radical concept suggests the universe could resemble a hologram. This isn't in the fantastical sense of shimmering illusions, but in a rigorously mathematical manner. As per the holographic principle, all occurrences within our three-dimensional space might be encoded onto a distant two-dimensional periphery, much like a hologram stores a complete image on a flat plane. In this scenario, the actual boundary of our universe isn't a physical barrier, but an informational threshold. This doesn't imply simulation or digital manipulation, but rather an alternative description of identical physical phenomena. Originating from string theory and black hole thermodynamics, this notion remains speculative yet highly captivating. The profound insight from these theories isn't a prediction of discovering a physical barrier at the cosmos's periphery, or a sign declaring end-of-universe authorized personnel only. Rather, it posits that space could possess limits and boundaries that deviate from our conventional understanding. Edges might reside within higher dimensions, within the universe's initial configurations, or within the foundational information of existence. They might not appear as physical walls. Instead, they could manifest as shifts in physical laws, alterations in curvature, or changes in the inherent rules themselves. It is entirely plausible that we inhabit a universe completely without edges. However, it's equally possible that we are confronting concepts that feel like boundaries, the limits of our knowledge, our observational capabilities, and our mathematical descriptions. And that too constitutes a form of boundary. Wouldn't you agree? As beings developed to exist in contained spaces, surrounded by air, gravity, and finite objects, we approach cosmology with these innate predispositions. We seek boundaries because they are ubiquitous in our lives. Yet, the universe, as always, is not bound by our preconceptions. Perhaps the cosmos gently folds back upon itself. Perhaps it extends infinitely in every direction. Perhaps it rests subtly on the surface of a higher dimensional bubble. Or perhaps, just perhaps, its form is something utterly beyond our current imagination. Something that curves, intertwines, and folds in ways our intellect can barely commence to fathom. And despite this, here we are, adrift in that enigma, contemplating boundaries while being an integral part of something potentially boundless. There is a certain tranquility in that thought. Don't you agree that the universe might be limitless, not merely in its extent, but in its very potential? Merely comprehending our own universe, with its countless galaxies, spiraling black holes, cosmic background radiation, and potentially endless curving space, presents a substantial challenge. We are already furnished with abundant subjects for contemplation. Nonetheless, occasionally, cosmologists and physicists are inclined to provoke further thought, posing an even grander question. What if our universe is not singular? This introduces the multiverse hypothesis, among the most captivating, peculiar, and utterly speculative concepts in contemporary physics. It proposes quite straightforwardly that more than one universe could exist, perhaps numerous more, potentially even an infinite number. Universes governed by distinct physical laws, comprising different particles, following separate timelines. Universes where felines traverse ceilings, gravity operates laterally, or your adolescent hairstyle decisions proved far more auspicious. Prior to delving further, let's establish a clear understanding. There is no direct empirical proof confirming the existence of other universes. None whatsoever. We have neither observed them, quantified them, nor communicated with them across any dimensional divide. The multiverse represents a conceptual framework, not a definitive finding, a mode of thought emerging organically from specific theories, yet firmly rooted in the realm of conjecture. Nevertheless, the notion is not as outlandish as it might initially appear. Indeed, multiple distinct interpretations of the multiverse hypothesis exist, each offering its unique cosmic vision. The primary and most accessible is termed the cosmic multiverse or bubble universe model. This concept originates from inflation theory, detailing the rapid expansion immediately following the Big Bang. Per this viewpoint, inflation did not proceed uniformly. Instead, it could have generated numerous discrete bubbles, each subsequently forming its own universe, expanding and developing autonomously. Each such bubble might adhere to its own set of physical laws. Some could be too alien to sustain matter, while others might feature entirely different species of particles, forces, or even spatial dimensions. We, fortuitously, inhabit one where conditions are precisely conducive to stars, planets, and extensive nocturnal discussions. Within this bubble paradigm, our universe resembles an individual soap bubble adrift in a cosmic froth. Other bubbles could exist, perpetually drifting, eternally isolated from our own. If you envision a celestial basin filled with dish lather, you are not far from the mark. Subsequently, there is the quantum multiverse, derived from interpretations of quantum mechanics, specifically the many worlds interpretation. This perspective posits that whenever a quantum event presents multiple potential results, all of them actualize in distinct branching universes. Thus, in one universe, you engaged the snooze button this morning and remained in bed. In another, you rose early and prepared pancakes. In yet another, your attempt at making pancakes inadvertently led to the discovery of teleportation. Each divergence establishes a novel rendition of reality, forged by the realization of every conceivable choice and contingency. This is no mere mental exercise. It is a significant interpretation of quantum mechanics developed to circumvent the complexities of wave function collapse. However, akin to the bubble universe concept, it remains beyond current empirical verification or observation. We lack the ability to traverse these branches. There exists no interdimensional terminal, complete with a mustachioed ticket agent, offering journeys to the universe where you achieved renown as a harmonica virtuoso. And indeed, within at least one of these boundless branches, you likely possess a moustache, regardless of ever having cultivated one. Statistically, it is practically assured. Somewhere in the expanse, you might be delivering a TED Talk on the ramifications of alternative facial hairstyles across parallel timelines. Furthermore, there is the mathematical multiverse, posited by cosmologist Max Tegmark. This theory asserts that all mathematically coherent structures inherently exist as physical realities. In essence, if a scenario is mathematically feasible, it manifests somewhere. This extends beyond universes with distinct particles to include those governed by entirely different logical principles, universes where the constant pi holds a different value, or where time progresses in a spiral. It is an audacious proposition, almost mystical in its breadth and likely beyond empirical validation. Yet, it is captivating to consider that mathematics itself might constitute the essence of existence, generating every conceivable permutation of reality like an inexhaustible archive of cosmic schematics. While these multiverse concepts are compelling, they appropriately encounter critiques. A primary concern is falsifiability. If other universes remain perpetually beyond reach, how can they be investigated? How can their existence be ascertained? Scientific progress thrives on the ability to test hypotheses, quantify outcomes, and refine theoretical models. When discussing domains unreachable by any discernible signal, applying standard scientific methodologies becomes challenging. Some physicists perceive the multiverse as a cautionary indicator, signaling theories extending beyond their practical boundaries. Conversely, others contend that the multiverse elucidates why our universe exhibits its specific characteristics. If innumerable universes exist, each with varying constants and laws, it is unsurprising that we inhabit one conducive to life. This represents a cosmic manifestation of survivorship bias. We exist here because this environment permits existence. It is somewhat analogous to rolling dice in a casino, featuring an infinite array of tables. Most tables yield unremarkable outcomes, but at one, by sheer fortuity, the dice align perfectly. That is the table at which we reside. We neither cheated nor manipulated the odds. We simply happened to be in the location where the numerical results were favorable. Certain cosmological models even propose that multiverses might be indirectly discernible, perhaps through anomalous formations within the cosmic microwave background, resulting from collisions between bubble universes. To date, no such evidence has surfaced. Nevertheless, physicists maintain an open perspective. After all, many of science's most extraordinary breakthroughs originated as unconventional notions awaiting the opportune investigative instruments. Regardless of whether other universes exist, their contemplation expands our imaginative capacities. It compels us to consider possibilities beyond our visual perception. It underscores that reality could be far vaster, more enigmatic, and more capricious than previously assumed. It calls for both humility regarding our unknowns and audacity in pursuing future discoveries. And fundamentally, isn't this the essence of science? Not merely providing answers, but uncovering profounder questions, not solely accumulating knowledge, but intensifying wonder. Even if another universe is never found, even if this one comprises all there is, humanity has already demonstrated its inquisitive reach across galaxies, through time, and into concepts as immense as the multiverse itself. That is a considerable achievement. Therefore, whether you subscribe to a single cosmos or an endless array, whether you favor one timeline or a branching multitude of quantum possibilities, remember that somewhere within the multiverse, you are engaged in something brilliant, unconventional, or inexplicably involving a llama. And in this particular universe, you are here, contemplating space, enjoying a beverage, and silently pondering what else might lie just beyond the frontiers of our current understanding. That, in itself, embodies a form of cosmic enchantment. Where does space terminate? This is the query that initiated our discourse, posed as gently as a child inquiring if the sky concludes. After venturing through galaxies, curved dimensions, the murmurs of cosmic microwaves, and the potentially existent boundaries, we softly return to our starting point, still contemplating. We've discerned that space does not behave like an enclosed chamber, a container, or a linear pathway. It lacks fencing or a finish line. Its completeness is not predicated on walls. It can be limitless or finite yet unbounded. It possesses the capacity to expand, loop, curve, and fold in ways our intellects are only beginning to fathom. It can even propel galaxies away from us at superluminal speeds, not due to their individual motion, but because the spatial expanse between us is elongating. We recognize the existence of an observational limit, a cosmic horizon beyond which light has yet to reach us. However, we remain unaware of what lies beyond this frontier. Perhaps the universe extends eternally, or perhaps it gently folds back upon itself in an arc we will never perceive. Our universe might be a single bubble amidst a multitude, drifting in a higher dimensional expanse. Or perhaps the multiverse is merely a poetic construct, beautiful but unattainable. What we do comprehend is that space is not void. It pulsates with structure and subtle energy. It expands with time. It transports the luminescence of primeval stars and the Big Bang's resonance. It possesses no central point and, as far as we can determine, no ultimate end. Yet, questions persist. Is the universe truly infinite or simply immense? Is it curved, flat, or something entirely distinct? Is it singular or one of many? And if space did possess a boundary, what would lie beyond it? We may never uncover every answer, but this is not a deficiency. It is the fundamental rhythm of scientific inquiry. The cosmos' splendor resides not merely in what we ascertain, but in our profound unknowns. It lies in the quiet fortitude of gazing skyward and asking. Regardless, the quest endures, as it always has, through instruments and equations, through serene reveries and nocturnal reflections. Each photon captured, each map constructed, each model refined brings us marginally closer, even if the ultimate destination consistently shifts like the celestial bodies. Perhaps that is the very essence of it. Perhaps space never ceases, not because it is infinite in magnitude, but because it is boundless in its mystery. Perhaps its significance doesn't hinge on an ending. Perhaps it simply exists, quietly sprawling in every direction, an invitation, rather than a confinement. Earlier, I posed several inquiries: your listening location, the current time, and whether the question, "Where does space cease?" might induce wakefulness or soothe you to slumber. My hope is that by now, you experience a greater sense of calm. I trust your reflections have settled into that tranquil realm where curiosity resides. And if you remain awake, if only just, I hope you discovered a measure of serenity in posing the question, even if the definitive answer remains beyond reach. For truly, that is the essence of space's gift to us. Not merely stars or quietude, but the liberty to explore the most profound questions of existence. And perhaps space never truly ends because questions, similarly, are boundless.